Welcome, ladies and gentlemen. May I have your attention, please? Thank you. Let's go ahead and get started. We've got a big day today as we embark on our Unit 7 journey. We'll be investigating the calculus of growth and decay. And so we're talking about exponential growth, exponential decay, separable differential equations. So we've got lots of neat stuff on the way and a variety of real-world applications. Such is the subject of your Moodle post this week. So there is a Moodle post. Thanks to those of you who are already posted. You can check out some real-world examples of how the rate of change in certain quantities are directly proportional to the amount of that quantity. Okay, so we're going to investigate one such case today to kick off our party with differential equations and exponential and logarithmic models. But first, let's go ahead and take a look at our Bellwork. So, what can we do to save time and energy, right, when differentiating or integrating with logarithmic functions? Well, oftentimes we can rewrite using our logarithmic properties, and then that makes our calculus lives easier. What do I mean by rewrite? Well, if our original expression y is given by the natural log of e to the 5x, recall that natural logs and exponential with base e's are inverses of one another. So the natural log of e to the 5x is equivalent to simply 5x. You could do that, you could verify that using log of a power property by bringing down that exponent 5x in front of the natural log as a multiplier. That would be 5x times the natural log of e. And we know the natural log of e is just 1. And so either way, right, we can rewrite y as 5x. And why is that useful? Because now my differentiation is very simple. I don't have to use a chain rule, right? I don't have to, with multiple links, I can simply differentiate 5x with respect to x and get 5. Raise your hand if you have number 1 is 5 already. Yes, yes, good job. Number 2, what's the relationship between the two distinct parts in my integrand function? That is cotangent of x and cosecant squared x. Right? What's the relationship between those two pieces? Hayden?
Cosecant squared x is the derivative of cotangent of x.
Yes, almost, right? Almost. Cosecant squared x is
Opposite.
almost the derivative, right? We just need a negative sign. So if we had that negative sign, we know exactly where that came from. Absolutely, thank you. So if we had a negative sign, we know that that would come from the cosecant squared. Negative cosecant squared would be the derivative of cotangent x. And so we could use that as a power function currently with an exponent of 1. Add 1 to the exponent, divide by the new exponent. But did I have that negative? No. So we need to account for that in our antiderivative by including a negative. We can add 1 to our exponent, divide by the new exponent. And what must we always include when evaluating indefinite integral? Right? What do we always have to include, Colin?
Plus c.
A plus c. Awesome. So we get negative cotangent squared x over 2 plus c. Go ahead and raise your hand if you had that. So anybody else have that already? Good job. Uh-oh, what happened?
Oh.
Did you miss the negative? Did you go turn by turn? Did you try and use the product rule? Tell me you didn't try to use the product rule. Recall that we have developed a product rule that works for differentiating, right? Differentiating. In this case, we were evaluating an indefinite integral, right? When we evaluate an indefinite integral, are we differentiating? No, we're integrating. We're anti-differentiating. We're going backwards. And so while we have a derivative rule for products, we do not, bless you, we do not have an antiderivative rule for products. As a matter of fact, we will develop that. It's traditionally a Calc 2 topic from colleges and universities. We're going to develop that after the AP exams. It's not included in the AB curriculum, but we're going to develop a technique for integrating products of functions. It's known as integration by parts, and it's typically a Calc 2 topic, just to give you guys a little leg up, right, on your classmates as you go off to the college and university world next year. You already know about integration by parts. All right, what questions do you guys have on number 2? Tyler.
I had negative 1/2 cosecant squared x plus c.
Okay.
So why doesn't that work?
That's a great question. So Tyler said he has negative 1/2 cosecant squared x plus c.
Yeah.
So what's going on there? Well, if we differentiate that, won't it produce the same? Right? If we were to differentiate, did you say negative 1/2?
Cosecant squared x.
So how come this is not an antiderivative of my original? Well, let's check. We know we can differentiate. We can differentiate this potential antiderivative and see if it produces the original result. And when we do that, we get constant multiplier -1/2 times, and we utilize the power rule. The derivative of cosecant squared of x with respect to x is exponent 2 times the base, that's cosecant of x, raised to the 1 less, that's to the first power, and then times the derivative of the base, right? The derivative of cosecant is opposite cosecant x cotangent x. And as I consider, right, this differentiated expression, I notice that my negatives disappear. Right, my negatives disappear. The 1/2 times 2 is just 1. And aren't we left with cosecant times cosecant is cosecant squared, and cotangent is cotangent? So isn't that equivalent to the original black before we did anything? Right? Isn't that original? So what's going on here? Did Tyler make a mistake? No, we verified that that is in fact the derivative of his blue antiderivative. Therefore, right, it's correct. So then, is this incorrect? No. No, what's happening? How could these both be right? They're both right. How could they both be right? They're both correct. Brandon.
We're seeing the magic of calculus. There are multiple answers to the same problem.
Well said, well said. It's only taken until February. The beauty of calculus has arisen for all to see. Thank you, Brandon, for pointing that out. Yes. How are these two equivalent algebraically? Well, isn't cotangent squared, right? Isn't cotangent squared related to cosecant squared somehow?
Oh, trig identity.
Yeah, remember when we see sums and differences and squares with our trigonometric functions, oftentimes that's a clue that it's a Pythagorean identity. And so if we were to rewrite this cotangent squared, right, as its Pythagorean identity, that would be cosecant squared x minus 1 right here for cotangent squared. I keep the negative. We keep the 1/2. We keep the plus c. How is negative cosecant squared minus 1 all over 2 plus c equivalent to Tyler's antiderivative? How are those equivalent? Are they equivalent? Yeah. Can I distribute the negative through and get negative cosecant squared x plus 1/2 plus c, right? And then that c is a constant. I could group in that plus 1/2 with my unknown constant c, and they would be equivalent. And so that c is just a constant, right? That c is just a constant, so we get exactly the same thing. So both of those antiderivatives, right? Both of those antiderivatives are correct. Nice job. So did anybody else think Tyler? Is that going to make me feel a little better? Oh, good. Hey, that's better then. So some of you didn't get this, but it's equivalent to that, and so that's correct too. I'll count. I'll take it. What questions do you guys have about 1 and 2? Then let's switch gears and get ready for today's exploration into the realm of differential equations, right? Differential equations and exponential growth and decay. So can we solve number 3 for x? Absolutely. It's very different than solving number 4 for x. And number 3, we've got a power function, and so we can rewrite this using our properties of exponents. This would be 4x to the 5th equals 11. So x to the 5th would equal 11/4, and so x must be given by the 5th root of 11/4. Raise your hand if you have number 3 correct. Do you have number 3 correct? Yes! Well, that's good news. Okay, so we can solve a power function. How is that different when we go to solve an exponential function, where my variable is not in the base of a power, it's rather up in the exponent? There's my independent variable. Well, in general, we want to add or subtract, multiply or divide to isolate the exponential, and then we get to utilize our logarithmic properties. Good thing we just spent unit 6 dealing with logarithmic properties. So my best first step would be divide both sides by 1,500 and generate 37 over 150 equals e to the, oh gosh. How do we get that variable down out of the exponent? Right? How do we get that variable down out of the exponent? Natural log, comma, maybe. So we can take the natural log or any log on both sides, but when we're working with base e, it makes sense to take the natural log on both sides. Then the natural log of e to the is just the to the. So this undoes, right, the natural log of e to the something gets you just that something down the ground floor. So natural log of 37 1/50 equals negative 0.0578x. One step to go, divide both sides, and I get x equals exactly natural log of 37 1/50. Close input all over negative 0.0578x. Uh-oh, we just solved for x by dividing by the constant. Negative 0.0578. And as a decimal, did you guys change it to a decimal? Because there are already decimals in there. So let's go ahead and see what that is about. And then I'll check with you. So natural log of 37 1/50. Close over negative 0.0578. And raise your hand if you got about 24.217. 24.217. Hey, great job. That's what I got. That's what I got. Awesome. What questions do you guys have about today's Bellwork? Okay, then we've got a double-decker to take care of for our homework check. But first, we closed out our discussion in Unit 6 with a roaring rendition of the elevator game. Recall that we could also call the elevator game going up or going down. In number 1, we were presented with a Bellwork question to go down one rung in the elevator if we differentiated, right? If we differentiated, what if number 1 had been an antiderivative problem? That is the indefinite integral of natural log of e to the 5x. Right? What if we were going the other direction? Would that limit our use of logarithmic properties for a potential rewrite? Because now we're integrating? No, we could still utilize our logarithmic properties to rewrite my integrand function. That would result in an easier expression, right, for which I recognize the antiderivative rule, and then anti-differentiate. And so again, whether we're going up the ladder or down the ladder, I encourage you to examine your original expression and rewrite using algebra, or logarithmic properties, or exponential properties, or trigonometric identities, to result in an easier calculus problem, right? To make your calculus lives easier. So I would certainly rewrite this as the antiderivative of what's natural log of e to the 5x? It's 5x. Isn't this integrand, right, easier to find an antiderivative for than natural log of e to the 5x? Most certainly. And so again, by utilizing logarithm properties to rewrite, you can make your calculus lives easier. I'm going to add 1 to the exponent and divide by the new exponent and get 5 times x squared. Not, of course, neglecting to include the plus c. Awesome. And so we could certainly, right, we could certainly find an antiderivative to the blue squiggle underlined integrand function more easily than the original. Awesome. Just something, to keep in mind. What questions do you guys have about our Bellwork discussion? Thank you, Tyler. I appreciated your addition to the Bellwork discussion. And Brandon, that meant a lot to me. All right, double-decker today. Ladies and gentlemen, let's go ahead and take out our review OTL. This was the second page after our concept and skill guide. There's another page that included a list of review problems. Let's go ahead and give yourself credit for those you completed out of 34. This is your review assignment only. It's not your prerequisite skill review. Good morning. Give yourself credit for those you completed out of 34, please. There's a staple on the front table and the side table. There's a graph. I'm going to pause this while I staple. Okay, ladies and gentlemen, thank you for your help grading your assignments. I appreciate that. So what's up with Unit 7? Unit 7 is all about differential equations. While that sounds super big, differential equations, that just means an equation that involves a derivative. And that should be old hat for you. In fact, you've already seen some differential equations already. When we have equations with y prime in them, that's already a differential equation, right? So what we're going to do is investigate differential equations. We're going to be able to solve a particular type of differential equation known as separable differential equations. Separable differential equations are the kind you'd be expected to solve on the AP exam that we'll be taking in May. So separable differential equations, we'll figure out what is that makes it separable. We'll figure out techniques to solve them, and then we're going to go ahead and checking out their general solutions versus their particular solutions and how they can help us answer real-life questions. We'll also be looking at slope fields. Slope fields, you could think of almost as the current in a river, right? If you were to drop a leaf out in the middle of the river, right? Most rivers have varying fluid flow through them. If you're close to the sides, maybe the current's flowing a little bit more slowly. If you're out in the middle, it might be flowing more quickly, depending upon the presence of sandbars or a turning river, right? There might be eddies and whirlpools and so on and so forth. And so if you're to drop this leaf into the middle of the river, where would the current take it? We can think of that kind of as an analogy for a slope field. Depending upon what initial point you know is on the graph of the solution curve, the individual slopes in this slope field would push that point along, and you could then use that to sketch a general solution to a differential equation. We'll talk about slope fields and how they relate to differential equations and their general solutions as well as their particular solutions. And then exponential growth and decay. A major application of calculus and mathematics includes exponential growth and decay. And while we looked at that a little bit last unit, we're going to look at it more in Unit 7. So that's kind of an overview of where we're headed. Again, the unit's not very long, and so it's not a very long unit, kind of like Unit 6 was pretty snappy. Unit 7 goes along fairly quickly too. And so I just opened up Moodle. You can check out the schedule. It's all up, including the keys and everything I just highlighted yesterday after the last testers. Okay, so today we're going to investigate exponential growth and decay, and we're going to use a famous differential equation in which the rate of change of a given quantity is directly proportional to the amount of that quantity present to set up our separable differential equation. So today we're going to earn stamps on 3A, 4C, 6B, and 7. We do need to come together for this famous differential equation and its general solution. It'll also be the subject of your Moodle post this week. So please make sure that you scheduled in your cell phone calendar, your personal planner, that you have a Moodle post this week. And this topic of today's activity is directly applicable to your Moodle post. Awesome. After you've circled the stamped eligible items, I'll go ahead and pause the recording. If you guys are scooting to your groups and get going right away, we have to come back together at about 35. So we've got just under an hour, okay, for closure. Thank you, ladies and gentlemen. Let's go ahead and consider our closure today. And so if the rate of change in y with respect to time is directly proportional to the amount y with constant proportionality k, then a differential equation relating y, t, and k can be written by. And so what I did is I gave you a little template here. These are intentionally on different levels. So this is supposed to be a fraction bar, and this is supposed to be a fill in the blank. Okay, and so here we go. Let's go ahead and rewrite that written expression in words. Let's rewrite that as a mathematical equation, differential equation. What would that look like with mathematical terms symbolically?
Y prime,
We were just going to answer.
oh, okay, Y prime is KT.
Right, or we use differential notation.
Oh,
Just like the DMT.
dy on dx equals of dy over dt equals. Yeah.
Proportional to the amount of that quantity present. Proportional to the amount
Oh,
of-
dy.
Okay, go ahead and share your differential equation with the class. Riley F. Cursive.
dy over dt is equal to k times y.
The rate of change in y with respect to time is directly proportional to, that means k times the amount of that quantity present, that is y itself. Go ahead and take a look at your differential equation. Raise your hand if you have dy dt equals k times y. Great, thanks, hands down. This is super important. This is saying the rate of change in a given quantity is proportional to the amount of that quantity. We've got a variety of real-world examples, right, that exhibit this scenario. And so we've got Marissa said the rate of change in a bacteria population is directly proportional to the number of bacteria. Well, that makes sense. The more bacteria there are in the petri dish, the more they can multiply, right? And the more quickly the overall population grows. Sydney had the rate at which coffee comes out of the Starbucks carafe with little pitcher thing is directly proportional to the amount of coffee in there. If there's more coffee in there, right, that's going to exert a stronger force downward. It's going to come out more quickly as it gets less, right? If there's less and less coffee in there, then it's going to come out more slowly when you open the stopcock. And then Michaela, stopcock, it's on the recording. Michaela said the rate of change in the number of molecules inside the balloon that isn't tied is directly proportional to the amount of molecules in the balloon. What? Well, yeah, right? If there's more air in there, then that balloon is shrinking more quickly. It's escaping more quickly, and so the rate of change in the number of molecules inside the balloon is directly proportional to the amount of molecules in the balloon. This is a super important differential equation, and that's the subject of your Moodle post this week. Okay, so if you were to solve this, for y, right, and get a regular function, y equals, what would that look like with our newly found, right, with our newly found labels? We're still using y, right, k, t, and we'll assume we have initial value a. So what would that look like as our solution, our general solution to this differential equation? Tyler?
Y equals AE KT.
Absolutely. Y equals a times e to the kt, where k is my constant proportionality. A is my initial value of y, right? The value of y when t equals 0. Y is the amount after t units, and so on and so forth. So what I want you to do is go ahead and raise your hand if you had that first. And then keep your hand if you recognize this general formula from pre-calc. And where have we seen that general formula before? And FST. And where have we seen that before? Sammy? A Pert, right? What we affectionately call A Pert, where the amount in my bank account is, right, given by the principal investment times e to the RT. This is A Pert. We're going to apply that in a variety of contexts. Way to go, you guys. I'm going to stop the recording and save it.